do we really understand what is happening with the phantom zero and how we can limit the bandwidth with the phantom zero? So here again is the transimpedance amplifier. Now we have compensated the thing with 50 PF and all the values are given below. And here is the expression for the transfer, for the current transfer from to the output voltage. So you see the transfer can be written according to the asymptotic gain model. If we ignore the direct transfer as, and in this case, direct transfer, by the way, will be zero. So the transfer can be written as the asymptotic gain times the servo function, which is completely defined by the loop gain, minus L divided by 1 minus L is the servo function, where L is the loop gain. Now, what was a phantom zero? A phantom zero was a pole in the asymptotic gain, and the pole in the asymptotic gain that coincides with the zero in the loop gain, which means that the phantom zero cannot be observed in the gain. That is strange. If I would put a capacitor there in CF and I implement the phantom zero, then I might wrongly conclude from this that I don't see the effect of CF in the gain. But we know better. We know much better. So this apparently is a contradiction, because if we replace the controlled source E1 with a nuller, then we see in the ideal gain there is the effect of the bandwidth limitation of CF. So here the ideal gain, so with a nuller in it, is minus RF divided by 1 plus S RF CF. So we definitely see a low pass characteristic set by the time constant formed by CF and RF. So what is the point here? How can we see a bandwidth limitation while, at the other hand, we state that the phantom zero is not visible, not observable in the gain because it is a pole in the asymptotic gain coinciding with the zero in the loop gain and thus cancelling in the expression V out over I1. That appears to be a contradiction. So in order to understand what is happening here, it is good to look at the root locus plot. So we will study the root locus plot of this system. And we do it here. We have two poles, one in the origin and one formed by the RF and CS. And then we make a phantom zero at formed by RF and CF. And that is the zero that you see left from the two poles. Now let's draw the root locus. That means let's, for increasing gain of the controlled source, which is this E1, plot the trajectory of the poles that they trace out in the complex plane. And I hope you still remember that in such a case, both poles move towards each other, then leave the real axis, make a circle around the zero, arrive at the real axis again, and one will move to the zero while the other will move to infinity. If the loop gain is infinite, then the one moving towards the zero will be on top of the zero, and the other one will be found at infinity. So yes, if there is one pole ending on the zero, and we had already the pole of the asymptotic gain there, we have two poles on the zero in the transfer, and one zero, so remaining one pole. And that's what you see. If you study correctly the behavior of an amplifier as shown here, and the loop gain would not be infinite, but the pole positions would be as indicated, so two poles on the right from a zero, so the zero left from the two poles, you will find the minus 3 dB point at a little bit higher frequency than the frequency of the phantom zero, because it never ends on the zero if the loop gain is not infinity. It moves towards the zero, and only at infinity it will be on top of it. So that is basically what is happening. That's why, let's say, if you make, basically, if you would limit the bandwidth, we're making a transfer with a pole, We're making a kind of active low-pass filter, a first-order active low-pass filter. Then the bandwidth of this low-pass filter is given by the servo function, and the pole of the servo function goes to infinity. You see, one pole goes to the zero, it will cancel with the zero, and the other one will go to infinity. So one of the poles of the loop gain moves towards the phantom zero. There was already a pole on the phantom zero, so we have the remaining one as the visible one. And this explains the bandwidth limitation. And the servo function gets a larger bandwidth, increasing with the loop gain. Maybe it is helpful to study this as well in the Bode plots. So here again, we have this transimpedance amplifier, and I'm now going to increase the feedback capacitance from 50 PF to a larger value to limit the bandwidth and see what will happen in the Bode plot. That is now of our interest. So here you see the situation in which the amplifier is compensated. If the amplifier is compensated and the zero is around the band edge of the two of the amplifier, so where the loop gain passes the 0 dB line, so the x-axis is the 0 dB. I forgot to denote it in the picture. So the x-axis is 0 dB for the loop gain, which means that there is one pole in the origin. You can see it. We already start with minus 6 dB per octave for the loop gain. Then we have a second pole somewhere. Then at the band edge, we put our phantom zero. So we are back to first order, and the transfer itself is second order because we don't see the zero. So this is happening when we are putting the zero. Look what I'm doing here. I'm putting the zero in the loop gain, zero, to a lower frequency. I'm passing it. This is the left line to a lower frequency. So I have more loop gain. You see, there's now more loop gain, and the servo bandwidth is enlarged. So when there is this zero, there is also this the gain dropping, as we just explained in the previous picture. So we are making our first order low pass filter here because this zero is implemented as this pole in the ideal gain. And you see the drop off at the gain of 6 dB until the servo function, of course, also drops. And then we have a second order roll off. So the difference is here, you see, it looks like a little bit like pole splitting, basically. And we can go on. If we bring the zero closer to the origin, we have this. The servo function gets more loop gain, gets more bandwidth, sorry. We are basically exchanging gain for loop gain. That is what we are doing. You see, look at the black line. We get much more loop gain. Much more loop gain means that at higher frequencies, we have more loop gain to suppress distortion, for example. And that can be really beneficial. So this is a good way of compensating. We are not throwing loop gain away by putting a capacitor somewhere in parallel with the signal path, as we did it last time. No, we are increasing loop gain, getting more quality, a wider bandwidth of the servo function, and that means you see that the first order characteristic of the blue line, which is the gain, extends to a higher frequency. And there, where the servo function drops, where it is minus 3 dB, there we have the influence of the second pole. So we can go on, of course, until in this situation we make the capacitor CF so large, because the pole was set by CF plus CS, but if CF becomes much larger than CS, then CS doesn't contribute to the pole anymore, and the pole and the zero are on the same place. So the phantom zero is really on top of a pole of the system, and that's the end of the story. We don't have more available than this. Our integrator, basically, our unity gain feedback integrator, because if CF becomes very large, it's just a short. So basically, the whole thing is the integrator with unity feedback, unity gain feedback. So I hope this explains a little bit what, well, not a little bit. I hope this fully explains what is happening with bandwidth limitation. But look, you see the increase of the servo function. Now imagine that I position a third pole somewhere, let's say between this step and the previous step, then the third pole would in the last step become part of the dominant group. So if there's a non-dominant pole and we are increasing loop gain, increasing loop gain, increasing loop gain, then the non-dominant pole at some time, at some increased value of the loop gain, might become dominant. And if this is the case, we have a second order system. Now, I didn't plot this here in this picture. I didn't plot another thing as well, which is that basically by putting CF there, the pole, the second pole, the first pole was in the origin, A over S, but the second pole was CF in parallel with CS with RF. So the second pole is also affected by CF, and the bandwidth was affected by CF, which means, and you can now see on, on my plot, the blue always ends on the same, but that is not true. The servo function the servo bandwidth will reduce a little bit, and also the gain will reduce. This is the case if CF can no longer be ignored with respect to CS. So that's something that is, oh, sorry, okay, sorry, yeah. So then there can be another effect, which is this non-dominant pole, another pole. So now I make this tau, this tau value for the third pole basically in the loop. I make it non-zero, and then we can study the effect of the zero. But I didn't put it in the plot. So non-dominant poles may become dominant, as I have explained in the previous sheet, and we will study this effect with the phantom zero bandwidth limitation in a Python version of SlideCap.